Hello viewers, in this video I would like to discuss you about the TSP, that is one of the famous problem named traveling salesman problem. So in this problem we have input as a distance metric and output as a permutation. What it means, input, let's say input, formally we can say that input is an in distance matrix where D is the distance matrix equal to Dij. I is for the matrix row wise. Row range is from 1 to n, and J is for the column, that is matrix column from 1 to n that belongs to natural number um, power n to n. So output will be a permutation. Permutation means a sequence of cities where city 1 to n 2 maps to 1 to n, such that we have a sum of distance of a permutation that is compared to a smaller or equal to the other permutation, this sum of distance of permutation of other cities. Now we have the permutation for all other cities is pi prime, that is 1 to n to 1 to n. Here the convention is that the permutation of n plus 1 is equals to permutation 1, means the position of first city is equals to the back city 1. So informally, what we say in traveling salesman problem is that given a number of cities and distance between each pair of cities, what is the minimum distance to visit each cities exactly once and back to the original city? That is the informal definition of TSP. Now, TSP, we already knows in my previous video I explained about NP hard and different kind of complexity problem. So, what is type of TSP algorithm problem? If you take the computation of TSP, you will see that for if it is a matrix of smaller numbers, like let's say matrix 4 by 4 matrix, then we can compute it into practically solvable time. But if you increase the input size of to n, then it is no more practically solvable time. It will be a factorial time of input size. That is bigger problem, and that situation is telling that TSP is NP hard, because though it has a good algorithm to solve, but still it does not have the algorithm to solve in practical time for my input size. And hence comes the point of TSPD. Then by TSPD is where you have a problem is called decision problem, and in TSPD is decision format of TSP, where input will be an intent distance matrix, and there will be also boundary value, that is then it will be a boundary value B. Now, in this case, the output will be yes if the permutation pi, or this sum of distance, pi of distance of a permutation is smaller than the boundary value, then there is a path. The output will be yes, or otherwise the output will be no. In this case, this TSPD will be solvable, can be in TSPD problem. We can easily see in the class of NP, which is called it can have We can solve it by a non-deterministic Turing machine. If it has a non-deterministic Turing machine that can guess a boundary value solution, and then it is easily possible to check in polynomial time that the permutations are other permutations are smaller than the boundary value or not. So and the most interesting part of TSPD and TSP is that we know that the definition of that NP complete problem, that first situation is called if any problem in class NP, then um, if a problem in class NP can be other polynomially reducible any problem to that problem, then that is called NP complete problem. In that case, we can say that TSPD is NP complete because we can polynomially reducible TSP to TSPD. This is in that case, so we can say that TSPD is NP complete. We can also say that TSP is also NP hard, and NP hard in a sense because we can polynomially reducible TSPD from TSP. So that's in a sense called that it is NP complete, but actually it is NP hard because it is not possible to solve in polynomial time the TSP. So that is interesting part. Maybe I will discuss in later video about these reductions. Thank you for watching this video.